Now we will use the k and tau we achieved from the previous lab to get the Kp and Ki we want to control the systems. Also, we will need the Kc and omega 0 to calculate out Kp and Ki. So if we set Kc as 0.75 and omega 0 as 16, we can use these formulas to calculate out Kp and Ki, and also the percentage overshoot and peak time for the second order response with this Kc and omega 0. Then we can calculate out the Kp and Ki as these two values, and also the percentage overshoot and peak time as these two values. Then we input these Kp and Ki into the control parameters and run the system. After we achieve 2 cycles, we will need to measure the real percentage overshoot and peak time. We can adjust the time scale. For example, like 5.2. Oh, it's too large. It's too small. Let's change it. 0.5. Then we can see here the percentage overshoot Okay, and then let's check the Y scale. Read from here. The Y peak is almost like 132, and Y0 or Y steady state is like 125. Then we can calculate out the percentage overshoot we measured as 5.6, and the peak time we can read from here. T0 is 5.0, and T peak is 5.19. Hence, the T peak time is T peak minus T0, which is 0.19. Okay, we can see the. Okay, let's adjust it here. Measured percentage overshoot and peak time are very close to our calculate out percentage overshoot and peak time. Meanwhile, it also asks us that what if we increase Xc and omega 0, which we used as 0.75 and 16. We can use these formulas to analyze their effects on the response. So we can see if we increase Xc, Kp will be changed and Ki will stay the same. That means it has this. It will increase Kp if we increased Xc only. So this is the effects if we increased Xc and if we increase omega 0, we can see from these two formulas, Kp will increase linearly, but Ki has a quadratic proportion of omega 0, so Ki will increase quadratically. Then, if we increase omega 0, both Kp and Ki will be increased, which will lead to here. So we can see if we increase both Kp and Ki, let's change this back first. Properties. If we increase both Kp and Ki at the same time, the system will become unstable, will become oscillating and then unstable. And that's true because we can see the effects here. Since Ki is increased quadratically, that means the system will go oscillating first, and then if Kp is increased, the system will become unstable. Then we will see the effects of the BSP, these parameters, on the response of the system. Here, let's set back the Kp and Ki values. So this should be 0.05. The BSP, if we increase BSP, that helps the measure the real motor response, check the reference better, and you can see on the response the red line. That means the real response will go to the steady state faster. And you can see the effects of BSP when the sine wave more clearly when the signal type is a triangle wave. Okay, let's turn it back to the triangle wave. Turn it to triangle wave and keep these settings and use these settings. One second. I will need to adjust the. Okay, it's back. Okay, we can see when BP is low, the real response just goes nothing. There's no real response. And if we keep increase BSP, the real response began to catch. Oh wait, it's silent. It's a triangle wave. When the input is when the reference is triangle wave and BSP is 0, there's no response, no real response. And if we increase BSP, the real response began to track the reference, and we increase it until it reaches 1. You can see right now the real response is almost match the reference. The difference between it comes from Ki. We have to increase Ki to integrate through that difference. You can see even a small Ki can overcome that difference. And when we increase, it matches better right now. I just changed nothing because it's already matched when K is very small. So this is the speed control with a proportional integral control system for the DC motor.